Good afternoon, everybody. I'm Vibhu Swain from Power Tech Consultant. Today, we'll start our webinar number 33. Let me share my screen with you. Okay, in this webinar number 33, we'll discuss about furnace, that is chapter 4 of book 2, that is energy efficiency in thermal utilities. What we'll do, we'll try to evaluate the furnace efficiency in indirect method in this class. This is an important uh, session, and where we need to understand how the furnace efficiency can be evaluated by indirect method. Now, we have already discussed the evaluation of boiler efficiency by indirect method. The furnace efficiency evaluations by indirect method is also similar to that of boiler. Now, what we have to do here, we have to calculate all the losses which are happening in furnace, and after that we have to reduce that losses from the 100% to find out or to evaluate the efficiencies. Now, in that case, what we are supposed to know, what are the losses in the furnace? Basically, one of the major important loss is sensible heat loss in flue gas, because furnace is heated at a very high temperature. So the temperature of the exit flue gas is very high as compared to boiler. So a substantial amount of heat loss occurs in the flue gas itself. Plus, as you know, in the flue gas, there may be some moisture in the fuel, in the air. So those will be converted to moisture. So there will be some heat loss, which moisture will take away. Also, the furnace has to open and close so that material can be put in and taken out. So there will be some heat loss due to opening of furnace. Then heat loss during through furnace skin and other unaccorded losses. Now, what are the typical range of this furnace or thermal efficiency? What are these range? Now, there are various type of furnace. One is low temperature furnace, in which you have batch type, continuous types. This is basically the temperature range at which this furnace operates, 540 to 980 degrees centigrade, at which the batch furnace operates. Similarly, coil annealing well radiant type furnace, strip anneal muffle furnace. These are basically low temperature furnace. Their efficiency is in the range of 20 to 30%, 15 to 25%. So also particularly for coil anneal, it is 5 to 7%. Now, high temperature furnace. Who are the high temperature furnace? Pulsar, rotary furnace, batch force furnace. They are also, you see, when the temperature goes up, efficiency goes down. That is mainly because there is a sensible heat loss occurring due to in the flue gas itself. Then we have continuous kiln like Hopman tunnel, where we can get a good efficiency in the range from 25 to 90% or 20 to 80%. Then also there are few ovens for heating, that is indirect fired ovens, which operate at 20 to 370 degrees Celsius. Direct fired ovens 20 to 370 degrees Celsius again, where the efficiency level is in 35 to 40%. So in the question, you may get some query, which are the efficiency of what type of furnace. So you have to remember this table little bit. And remember, the furnace range is normally industrial furnace efficiency range in the range of 35 to 40%, as you can see here. And when the temperature goes up, then automatically the furnace efficiency goes down. Now, what are the instruments required particularly to determine the furnace efficiency? What measurement exactly we need to carry out during energy audit period, what exact we need to do. Furnace consumes a lot of thermal energy, so a typical measurement has to be done. One is furnace soaking zone temperature. That means the material coming out, so heat has been soaked. So we need to measure the temperature of furnace soaking zone temperature. Then we have to measure the flue gas. That means the flue gas temperature, and the furnace soaking zone temperature can be measured with platinum rhodium thermocouple. These are special type of thermocouple which functions on the principle of thermoelectric effect. That means when you apply two metal junctions like platinum and platinum rhodium, they are two metals joined together at two terminals, and you heat and in one terminal and cool another terminal, then you will get some electrical effect, which is known as thermoelectric effect, due to which you get some temperature reading. So this is the principle of thermocouple. So furnace soaking temperature, zone temperature, we have to measure with platinum rhodium thermocouple. Flue gas normally is measured with temperature is measured with chromel almel thermocouples. Similarly, flue gas after recuperator, where the temperature has gone down a little bit, can be measured with mercury in steel thermometers. Furnace hearth pressure in the heating zone. So basically, low pressure ring gauge can easily evaluate the furnace pressure. Flue gas analyzer, you have to measure O2 or carbon dioxide and monitor the temperatures with the flue gas analyzers, because O2 measurement is required to know what is the excess air level and what is the dry flue gas losses. Billet temperature can be measured with infrared pyrometer or optical pyrometers. These are basically infrared thermometers. So, and these are all are portable instrument, and these are the location at which the measurement has to take taken. So we have to measure the temperature of billet. Flue gas analysis we have to carry out. Flue gas temperature we have to measure. Furnace zone take working temperature we have to measure with the available instruments. Now let us do these examples. An oil-fired reheating furnace has an operating temperature. Operating temperature of the furnace is 1340 degrees Celsius. The average fuel consumption is 400 liter per hour. Remember, this is in liters. It is not in kg. We have to convert it to kg by multiplying density. So I have multiplied 0.92. 92 is the density of the furnace oil, which we can remember. Otherwise, sometimes in the question the data will be given. Otherwise, density is 0.92. You have to remember, and this 368 kg per hour is the 400 liter per hour. That is the average fuel consumption. Now, flue gas exit temperature after air preheater. That means some heat recovery, waste heat recovery product has been employed or equipment has been employed. So after air preheater, the temperature of the flue gas is 750 degrees Celsius. Air is preheated, ambient is 40 degrees Celsius, and it is heated up to 190 degrees Celsius through an air preheater. Now, because of this air preheater, the ambient air is heated up. The furnace has 460 thick wall, that is X, and the billet extraction outlet, which is 1 meter dia and 1 meter width or wide. This is required to find out the opening thermal loss. So the opening is 1 meter into 1 meter, and thickness is 460 wall, and this is at the billet extraction outlet side. So we have to we have to find out the efficiency by both indirect and direct method. So what is the exit flue gas temperature? 750 as ambient 440, preheated air temperature 190, specific gravity of oil given 0.92. So this is a specific gravity. So if I multiply, I got average fuel oil consumption is 368 kg per hour. Now what is the calorific value of oil? It is 10,000 kilocalories per kg. Now oxygen is measured, that is 12% in the flue gas. So, and weight of the stock is 6,000 kg per hour. Specific heat of the bullet is 0.12 kilocalories per kg per degree Celsius, and average surface temperature of heating and soaking zone is 122 degrees Celsius. So these are all given data. Now let us find out What is the average surface temperature other than heating and soaking zone? It is 80 degrees Celsius. It is also given. Area of heating and soaking zone is 70.18 meter square, and area other than heating and soaking zone is 12.6 meter square. These are required to find out the heat loss from the surface. Now we have already remembered the formula. How to calculate if O2 is given? How to calculate excess air? The formula says it is O2 by 21 minus O2. So if I put O2 as 12%, then I'll get excess air is 133%. That means I am supplying 133% extra air to the furnace. And typically, now this figure, this is an important figure. If you go back to boiler calculations, we have already established how the theoretical air required to burn 1 kg of oil is 14 kg. Is based on the chemical composition of the furnace well, the content of H, content of C, and other parameter. We have established that. Now, if these parameters are not given, the proximity analysis has not been given, then what can be done? We can remember this as a thumb rule that 1 kg of oil required, theoretical air requirement will be 14 kg. Now, but what is this excess air? 1.33%. So that means 14 kg, the total air supplied will be 14 kg into 1 plus 1.33%. That means 100. That means 1 plus 1.33. So 2.33 kg of oil. So total air supplied will be this much of kg per kg of oil. So 32.62 kg of air is required per kg of oil. That is the air supplied, not air required. That is the air supplied. So what is sensible heat? Heat loss will be specific mass, specific heat, delta T. Now, what is the weight of the flue gas in this case? Weight of the flue gas is basically total air supplied plus the fuel. Fuel is basically 1 kg. And what is the weight of flue gas is basically air supplied is 32.62. So 33.62 kg of oil AM is we could find out. Now CP has been given, it is 0.24. And what is the delta T? Delta T is 750 because ambient temperature is 40, the furnace temperature is 750. If you can see here, exit flue gas, so it becomes 750 minus 40, it becomes 5729 kilocalorie per kg of sensible heat loss is there. Now let us divide this kilocalorie per kg of oil by GCV of oil. GCV of oil is how much? 10,000. So I got 57.29% is the heat loss, particularly in the flue gas. So this is a very huge loss. Almost 50%, more than 50% has been taken away by losses. Now you all remember this formula in the boiler. Percentage heat loss will be M 584, which is a latent heat, into Cp. The Cp is the particularly specific heat of the steam, and TFG is the flue gas temperature, T ambient is the ambient temperature, GCV is the calorific value. If I apply this M, then what will get? I'll get M he has taken moisture is 0.15 because this is the normal moisture in furnace oil, which we can remember. So 0.15 into 584 plus 0.45 is the specific heat of the moisture, 750 minus 40. So this becomes 1.36% is the heat loss due to evaporation of moisture present in the fuel. Now, so there is some fuel, the moisture is there. So when it gets contacted with oxygen, it becomes water. Then the water vapor is taken away. So it takes some heat loss. This heat loss is 1.36%. Now there may be some hydrogen in the fuel, and due to which this hydrogen will react with oxygen and form water. This water will be evaporated, taking some heat from the furnace. So this is the loss due to evaporation of water formed due to hydrogen in fuel. So this becomes 9H2. This is a formula what this is 9H2 into 584 plus Cp into TFG minus T ambient and GCV of fuel. Now what is the H2? H2 kg of H2 in 1 kg of fuel oil is 0.1123 kg of fuel oil. So it becomes H2. That means what is the H2 is 0.1123 per kg of oil we are calculating. So this much of H2 is there. So this is into 584 plus 0.45 into 750 minus 40. we could divide by GCV of fuel. It is 10,000. So this become, here we got almost 9.13% is the loss due to evaporation of water formed due to hydrogen in fuel. This formula also you have studied in boiler. And this H2 is basically 1123. These are the two important things you have to remember in this. Now, let us say if there is some opening, if some material is going out, again coming in, then what will happen? The door will open and there will be some radiant inside the furnace temperature is very high, maybe 750 degrees Celsius. So automatically there will be some radiant heat which will coming out from the opening. So some heat loss will also occur due to opening, continuous opening of the furnace. So in the industrial furnace, normally we are advised to close the furnace as soon as possible to avoid heat loss due to opening. Now, what is this heat loss? What is the value of this heat loss? For we need to understand the black body radiation losses. Now, let us go to black body radiation process. Physically, it is mentioned in 4.13. Then, so black body radiation temperature, if I get something, then I can know what is the black body radiation in kilocalorie per cm square per HR. So, what we have to understand? We have to understand what is the temperature. In this case, what is the temperature? So if I refer the temperature, it is the temperature is almost the factor of radiation is 0.71. The factor of radiation is 0.71 with furnace temperature of 1340 degrees Celsius. Now let us find out whether this is coming or not. Now 1340, it is in this range. So it is almost, this one is basically the temperature or is of the black body, total black body radiation factors. Now, now you come here basically. Now this factor is basically come from the D by X ratio, this 7.71. Now what is happening? The shape of the opening is square, so we have to, the X, that is the wall thickness has been given, that is 460 mm thick, and dia or the width or the height of the opening is also given, that is D. So we have to find out what is d by x. Since the opening is square, so d by x will be 1 meter divided by 0.46 meter. So it becomes 2.17. Now, based on this d by x ratio, we are supposed to find out the factor of radiations. Now, how to find out? It is very simple. This problem in the numerical, these books, it will be given in the book. Perhaps it is not there. So it is in the old books earlier it was there. So if I found out what is the d by x ratio, d by x ratio is 2.17. Now let us go to 2.17 in this scale. So if I go to the top, if it is square opening, so I have to take this curve. So square means, that means the factor, total radiation factor, I got it from 0.71. This is how from this equivalent heat release curve or opening to the quality of heat release from the perfect black body. From this black body curve, we can find out the factor. So in this case, it is 0.71. Now, black body radiation corresponding to 1340 is equal to 36 kilocalorie per cm square per hour. How we can get this? We can get it from figure 4.14. So this is 1340. So if I touch here, it will come something like that 35, 36. So this is the black body radiation curve. By measuring the temperature, I can find out what is the kilocalorie or heat loss per cm square per hour. From one surface area, what is the heat loss? Now, area of opening is how much? 100 centimeter into 100 centimeters. So it is 10,000 square centimeters. Emissivity is 0.8. So total heat loss will be 36. That's the blackbird radiation into 10,000 into 0.71, that is the opening, and 0.8 is the emissivity factor. So from this we could find out it is around 204480 kilocalorie per hour, which is nothing but, now this figure is basically, if I divide it by GCV of the oil, what is, how much that is? 10,000. So 20,000 24480 divided by 10,000, I'll get a figure almost 20.45 kg per hour. So this is the equivalent fuel loss that is 20.45 kg per hour, and percentage of heat loss through opening will be, what is this? 368. 368 is basically is the fuel. What is the fuel rate is going per hour? It is 368 kg per hour. It is going to the furnace. So how much of heat loss is happening or fuel loss is happening? 20.45 kg per hour. So what is the percentage of heat loss? This divided by 368. So 5.56% is the heat loss due to opening. So still now the boiler, the flue gas loss is very high. Now, so this figure is required to understand the d by x ratio. From the d by x ratio, once we calculate, this is d, this is the height, x is the wall thickness. If we calculate that, we can find out total radiation factor. These are very important. Remember it in the numericals, particularly chapter 4. We have to understand, and we have to, in the open book, we have to take use of these graphs. And this is the graph for determining black body radiation at particular temperature. As the temperature increases, the black body radiation also increases. But even at 1000 degrees Celsius, the black body is almost 40 degree or 40 kilocalories per cm square per hour of heat radiation is happening. Now, this is another formula or another curve in which, based on the temperature of the external surface of the furnace, we can find out what is the quantity of heat loss. This is another example or curve which we have to also remember. It is there in the old book. Now, this one is one. This is the ceiling. So, in the furnace, from the ceiling, some heat loss will be there. Again, in the side wall, some heat loss will be there, because if the temperature goes up inside, and since there is a wall thickness, the temperature is coming towards the atmosphere, and again in the atmosphere it is getting cooled. So, totally continuously some heat will be always taken in and taken out from the system. So, there will be some side wall, and hearth is also exposed to the other side, downside. So, from 1 to 3, that is ceiling, side wall, and hearth, some losses will happen. So, how to estimate this quantity of heat loss? That can be done by, from this graph, by doing this temperature profile uh, of the external surface. So, if the external surface, based on the external surface temperature, we can find out what is the heat loss for all these 1, 2, 3 parameters. Now, heat loss through roof and sidewall will be how much? Now, it is 120 degrees Celsius is given as the average surface temperature. Now, if it is 120 degrees Celsius, so let us example what is. So, this is almost in the ceiling or in the hearth, it will be almost 1150 or 1175 heat loss will be there. Now, in this case, it is 1252. So, let us say what is this one? It is basically, it is trying to find out what is the furnace roof and sidewall. So, 1252. Now, let us find out what is 1252. Now, if I see, this is 122 degrees Celsius, and what is the heat loss from the furnace or from the roof and sidewall, that can be found out from this. So, this is basically 1 is the ceiling, 3 is the hearth, 2 is the sidewall. Let us take this 2. So, 122. If I go like this, it will be almost in this range. I'll get. So, from this graph, I can find out this is almost 1252 degree or 1252 kilocalorie per meter square per hour. Now, what is the total area? Heating zone plus soaking zone, it is given 70.18. Now, heat loss parameter or the rate of heat loss we have also calculated. So, what is the total heat loss? This rate into area. So, this is 87865 kilocalorie per hour. Now, if I divide it with the GCV, that is 10,000, I can find out equivalent oil loss will be 8.78 kg per hour. Similarly, what is the average surface temperature of the area other than heating and soaking zone? It is 80 degrees Celsius is given. Now, at 80 degrees Celsius, what is the heat loss? So, let us see 80 degree, that means almost in this range. So, it is in the range of 80 degree means it is in the range of 600 or 740 kilocalorie per meter square per hour. So 80 is basically, if I get it will be in this will be around 700. So this will be in this range. So from this graph, he has found out the heat loss at 80 degree Celsius will be 740 kilocalorie per meter square per hour. Total area is 12.6 meter square. So what is the heat loss? Area into the heat loss rate. So from this we can find out 9324 kilocalorie of per hour heat loss is happening. So what from the furnace skin there are two heat loss. One is through roof, through sidewalls, and another one from other area other than the heating and soaking zones. So it becomes total heat loss is becomes this plus this, it is 9.71 kg per hour. Now if I divide it by 368, I can find out that is the particularly 2.6%. If I multiply with 100, I'll get a percentage of heat loss, that is 2.64. Similarly, unaccounted loss is also being considered. This may be due to furnace heat storage loss, due to loss of furnace gases around the charging door opening, heat loss by incomplete combustion, loss of heat by conduction through hearth, loss of due to formation of scales. So these are unaccounted loss which we are not considering at present, but there are certain formulas that are available. We can calculate that one. So if I ignore the unaccounted loss which I cannot account for, then what I'll get? I'll get furnace efficiency. Now already we have measured. Let us try this one first. Already we have measured sensible heat loss in the flue gas is 57.29%. Loss due to evaporation of moisture in fuel is 1.36%, and loss due to evaporation of water from H2 in fuel is 9.13%. 5.56% is the heat loss due to opening. 2.6% is the heat loss due to skin. So it becomes 75.98% is the total losses by indirect method. So if I reduce it from 100 minus 75.98, it becomes 24.0802% heat loss or the efficiency in indirect method. Now, what will be the direct method efficiency? We have understood direct method means it is not a loss method, it is heat output divided by heat input. So it is the heat output by heat input method. So what is the heat input? 400 liter per hour, multiply specific gravity, you will get 368 kg per hour. Now what is the heat output in that case? M Cp delta T. M is the mass of the billet, that is 600 kg. Specific heat 0.12, 1340 minus 40 is the delta T. So it becomes 93600 kilocalorie. So the efficiency will be output divided by input. Output is this much of heat. Input is this kg per hour into CCV of oil. So it becomes 25.43% is the efficiency. So losses is 75%. So if you can compare both these figures, these almost are equal, but here it is little bit it is little bit more practical or more accurate, where this is not so accurate. But anyhow, we are getting some parameters of efficiencies through direct method as well as indirect method. This is an important session, and basically what we have learned here, if I go back, I have to we understand, we have to understand this given data first, convert the oil into or liter per hour into kg per hour by multiplying specific heat. Then we have to remember this O2 minus 21 minus O2 formula to find out excess air. Then 14 kg you have to remember, otherwise if proximate analysis data is given, then in that case we have to find out whether it is 14 kg or 14.7 kg. So this again we have to find out, otherwise you can remember 14 kg. From that we found out air supplied, then we calculate the dry flue gas loss, then we calculate the evaporation loss due to evaporation of moisture present in the fuel, then loss due to evaporation of water present in the hydrogen, due to hydrogen particularly, loss of opening, heat loss due to heat loss due to opening. This is an important assignment which is not there in boiler, because boiler is a closed vessel, but here material is going in, going out. So you have to find out d by x ratio. You have to understand this curve, that is the to find out the total radiation factors by monitoring d by x ratios. and these are for square opening, round opening. Then this is a black body radiation. You have to understand what is the total black body radiation in kilocalorie per cm square per hour. From these two data, we can calculate the efficiency, and also you can calculate what is the total efficiency. Now this is the temperature of external surface of furnace vis-a-vis quantity of heat loss. So based on this formula also we can calculate the quantity of heat loss. Then we calculated the heat loss due to furnace skin, that is the sidewall roof, in which we considered that figure 4.26, and by multiplying the area into the heat rate, we can calculate the total heat rate divided by that fuel rate. We will get the total percentage of efficiency. From these we could find out by the efficiency by direct method as well as indirect method. With this I close this session today. I request that you all should understand, do numericals, and do these calculations, particularly for boiler, and then only will be able to do the numericals with the examinations. With this I close. Thank you and good day.